How are partial differential equations used in mechanical engineering? Imagine trying to predict how heat spreads through a metal rod, how a bridge vibrates in the wind, or how fluids flow inside a pipe. These are complex problems that involve changes across space and time. Mechanical engineers use a special kind of math called partial differential equations to understand and solve these kinds of problems. Partial differential equations are equations that involve functions with more than one variable, like position and time. They describe how physical quantities such as temperature, pressure, or displacement change in different places and moments. Engineers develop these equations based on physical laws like conservation of mass, momentum, and energy. For example, when analyzing heat transfer, they use the heat equation, which is a partial differential equation that predicts temperature distribution in solids over time. In system modeling, partial differential equations help create detailed models of real-world systems. Instead of just looking at how a system behaves over time, they consider how it varies across space too. This is especially useful when dealing with structures like beams or shells that have different responses at different points. In advanced topics and professional practice, engineers often solve these equations to simulate how systems will perform in real life, saving time and resources. When it comes to system dynamics and control, partial differential equations are used to model systems with distributed parameters. Unlike simple systems that depend only on time, these systems change across space and time. For example, controlling the temperature in a large industrial furnace requires understanding how heat moves through the material. Similarly, vibrations in large structures like bridges or aircraft wings are modeled with wave equations, which are hyperbolic partial differential equations. These help engineers predict natural frequencies and how structures respond to forces. Fluid mechanics is another area where partial differential equations shine. The Navier-Stokes equations, which are a set of partial differential equations, describe how fluids flow. Engineers use these equations to design efficient pumps, turbines, and aerodynamic surfaces. They also help analyze weather patterns and ocean currents. In structural analysis, elliptic partial differential equations like the Laplace and Poisson equations are used to model stress and deformation in materials under load. This helps engineers design safer, more durable structures. To solve these equations, engineers often start with analytical methods like separation of variables or integral transforms. But many real-world problems are too complex for exact solutions, so they turn to numerical methods like the finite element method or finite difference method. These techniques break down the problem into small parts, making it easier to approximate solutions for complex shapes and boundary conditions. Today, partial differential equations are integrated into system modeling tools that simulate how systems behave in real life. They help engineers design controllers, predict responses, and optimize performance. Whether working on thermal management, vibrations, fluid flow, or structural integrity, these equations are a core part of the toolkit. They connect theoretical analysis with practical design, making them essential for advancing mechanical engineering.